Bueno, lo primero quiero agradecer al comité científico y al comité organizador local, lo primero por invitarme y lo segundo por una organización completamente impecable, que la reunión está funcionando perfectamente. El máximo problema que he tenido yo en estos últimos 2 días ha sido tratar de decidir si voy a dar esta charla en español o en inglés. Hay razones buenas para darla en un idioma y en el otro. La razón principal por la que la voy a dar en inglés es porque creo que será mejor charla si la doy en inglés que en castellano. Y creo que eso es lo más importante. So I'm going to switch to English now, and I'm really sorry that I'm not doing it in Spanish in the Spanish Astronomical Society meeting, but I think it will be a better meeting, a better talk if I do it like that. So something else I wanted to say, if any of you was at the GENA meeting, at the Symposium of Morphology and Density, the talk I'm going to give now is a slightly expanded version of that one. So if you were there already, probably this is a good time to go to sleep. Try not to snore. Right, so galaxy evolution in clusters. First of all, I want to say that much of the work I'm going to describe here has been done in collaboration with 2 reasonably large consortia of people. One is the ESO Distant Cluster Survey here, and the other one is the STAGES collaboration, and I'll introduce them, and I will be giving credit where credit is due. So this is the overview of the talk, and I will try to motivate, I'll tell you a little bit of why we're doing all of this. And then I'm going to move to some results that we've obtained in the last almost 10 years from the European Southern Observatory Distant Cluster Survey, EDISCS, some highlights. And then I will concentrate on the morphology, star formation, kinematics, etc., the properties of galaxies as a function of morphology, what we've learned from that. Then I'm going to move to stages, and I'm going to explain a couple of the new results that we have there on transformation of spirals into S-zeros, probably, and what the environment does to galaxy sizes and galaxy structures, and then try to see if this is all fitting together into what we think galaxy evolution does in these environments. So we've already seen this before. Carlos Frank showed it. This is a dark matter simulation that tells us approximately, or probably quite precisely now, how the dark matter skeleton on which clusters of galaxies are built and galaxies on them grows. And one of the reasons why I'm showing it here is because I want people to stop having this idea that clusters of galaxies are nice, relaxed, spherical systems. They are not, right? They are part of this filamentary structure in which at the intersection of these filaments, large masses are concentrated, galaxies concentrate there. But the structure does not have to be spherical at all. And the other point that I want to make is that many of these structures are evolving today. They're not built, they're not finished. The evolution of clusters is happening today. So we do not have a final product in terms of many clusters. Some of them are more evolved than others, but just try to remember that. Okay, we saw that already, and many of you have. It's absolutely and utterly beautiful. So I just I wish we could have pictures of the real universe with as much detail as that. The advantage of the real universe is that it is real. Something else I wanted to show in terms of the simulations is something that it was not shown in the previous movie, is that whenever we see any of these dark matter simulation movies, we see them in comoving coordinates. What that means is that the expansion of the universe has been taken away. But you've got to remember that in the initial stages of a cluster, and I'm trying to find the mouse now, the universe is expanding, right? So at the beginning, the galaxies that are going to end up in a cluster are not actually falling. They're getting farther away from each other in the real space. And then later, they will fall back. But also to point out that this phenomenon of falling back can happen until quite recently, okay? And many of the clusters that we see are still being formed. Galaxies are falling onto them at quite large velocities, thousands of kilometers a second. And something to remember also is that if we see a very massive cluster today, if a cluster has got a very high mass, whenever we see it, it means that it must have formed very early on, because it needs time to build up the mass. So you cannot just have a very massive cluster that has just started forming today. It may not be the final stage, but if it is very massive, it must have started quite early. So the reason for this symposium in Lisbon at Genam was that it is now 30 years since Alan Dressler plotted this diagram here. And this is a diagram that talks about morphology. And I heard in the previous talk the best justification to do morphology that I have ever heard, which is that morphology doesn't explain anything, but it tells us what we need to explain. Fantastic. I wish I had thought of that, Nolan. That was a very good reason why to look at morphology. There is another reason when doing morphology of galaxies, is that when you look at them, they're very beautiful. So you look at them, and they're very pretty. I'm not completely sure which one is more important. Anyway, this is the morphology fraction on the left axis versus density here. Okay? This is high density, this is low density. And the lines, the blue line talks about the fraction of spiral galaxy, the black line, lenticular S0 galaxies, and the red line, elliptical galaxies. And we all know that in the densest regions, we find very few spirals and very few regulars, and we find lots of ellipticals and S0s. Okay, that's fundamental, that's very important. We've got no idea why is that yet, or we have some ideas, but we don't have a final explanation. And it is not clear yet whether the final result, which is here, comes from the intrinsic properties of the galaxies that correlate with environment, or whether the environment itself does the job. Now, there is a big debate now that is trying to decide whether the mass is the main thing that does everything, an environment that does nothing, or whether the environment still does something. I'm not going to enter that debate for the reason that I think that is mostly semantic, okay? And so I'm going to leave it there. But there is something also very important that was already present 30 years ago in this diagram that I want also to emphasize here. And is the red line and the black line are completely different, okay? So I'm going to make a plea here to the extragalactic astronomical community. Please do not think for a second that the lenticular galaxies and elliptical galaxies can be bundled together and say that they are the same, they form and they evolve in exactly the same way. Just this diagram is telling you that that's not the case. The black line and the red line are very different. The ellipticals are much more peaked at the center. The lenticulars increase more slowly, okay? So, yes, sometimes they look the same, yes. Sometimes they have the same colors, but no, they're not the same thing, okay? So try to bear that in mind. And clusters of galaxies are dynamical entities. This is a simulation for Cardiff of something as well known as the Virgo cluster, and you see that galaxies there fall into it and move around, and you got many ellipticals, and you got still some spirals falling onto it, okay? And that dynamical status of the clusters, the fact that galaxies move through the cluster in which they are going to encounter other galaxies, they're going to encounter dark matter, they're going to encounter gas, etc., may and probably does do something to the galaxies. So, why clusters? Well, if we want to understand what the environment does to galaxies, it's a good thing to look at the places where the environment is more extreme. Of course, one needs to look at all environments, and I think groups are very interesting. Isolated galaxies, as we heard about this morning, about the Amiga project, are very important, but clusters provide the extreme. They provide probably the densest regions of gas in which phenomena like the stripping of the gas via ramp pressure stripping, or what's called now extrangulation, where you just take only the halo gas, may remove the fuel for future star formation that may be important. Things like interactions with other galaxies, repeated interactions that were called by Ben Moore harassment, or mergers that may or may not happen very often in clusters because the galaxies are whizzing about very fast, but because clusters are not spherically relaxed, there are subclusters falling onto them and filaments in which the relative velocities may be less important, so mergers are maybe important. So all these things can be happening at the same time. And the problem is that if they can happen, I think that they probably do happen. And they're all happening at the same time. So trying to see which one is more important is not easy. And we do not know the answer yet. What I'm going to try to do in this talk is to show you what observational evidence we have from clusters. So first of all, credit where credit is due. We did the ESO Distant Cluster Survey that started, I can't remember how long ago now, but close to 10 years ago, from a large ESO program led by Simon White, and there's many people, several of them in this room, that have been working on this, on the observations, on the models, etc. I think for this talk I'm going to mention in particular the driving force of Bianca Poggianti, who has done a sterling job at understanding and explaining many of these things. So what it is, well, what we did is we chose an optically selected sample of clusters, and I'll tell you in a minute why, at redshift between 0.4 and 1, so that is, you know, trying to go and you compare it to redshift 0, you cover half of the age of the universe. And what we want to do is to find those clusters and get as much data for the galaxies in those clusters, or for the clusters themselves, as we can. And you can see in this picture, you got your typical cluster there, with your brightest cluster galaxy there, and you know, to see that these pictures are just ground-based from the VLT, about 1 hour images in several bands. You know, we've got several, the beautiful CD galaxy there at the center, clusters where actually there are lots of blue galaxies, and other clusters were just more typical, okay? So we chose these 20 clusters, and we threw at them as many observations as we could, and see what we could learn. One important thing is that we had extensive spectroscopy. The vast majority of the time we spent at the VLT was taking spectra, and spectra that are good enough to get redshifts, but also good enough to do some study on the star formation rates, on their stellar populations, and people like Patricia Sanchez-Blasquez, who's in this room, has done quite a bit of work on that, but also allows us to select the galaxies that are in those clusters, measure the velocity dispersions as a proxy for mass. And we found that not only we found those clusters, but also we found some other groups and smaller structures. And this is, I think, the main reason what makes the eDiscs sample special. In here, you can see look-back time, or redshift if you want, and here is velocity dispersion. This histogram here, the black histogram, gives you the velocity dispersion distribution of the groups in the local universe as determined from Sloan, okay? And the lines here tell you what the velocity dispersion of a cluster, what it does with time. That is, it grows. It grows a little bit because the mass of the cluster needs to grow. So from high redshift to low redshift, it grows. And the black triangles here are the eDiscs clusters. The red symbols and the blue symbols were previous samples in which Hubble Space Telescope studies of morphologies had been done. And you see why eDiscs is important immediately. Because if you want to represent, to find the counterparts, the progenitors of present-day clusters, you must do that by having low enough masses. And if you look at the ones at the top, by the time you get to today, well, there are precious few clusters as massive as that in the present universe. Okay, so they are not representative. The other important thing, of course, is how they range in velocity dispersion, how wide it is for eDiscs. That will allow us to study the dependence of any process on the mass of the cluster, on the velocity dispersion of the cluster. Okay. So the first thing that I wanted to mention is that the clusters are special environments, and we find there some galaxies that we find nowhere else. Only in clusters one finds the brightest cluster galaxies. Right? That's, of course, tautological. You cannot find brightest cluster galaxies outside clusters, but seriously, they are the most massive galaxies in the universe, and they've got a particular role because they live at the deep end of these potential wells. So what we've learned from those is a few things. The first is that most of brightest cluster galaxies have got colors that evolve pretty much passively. Their stars form quite early on, perhaps at redshifts of 1.5 or 2, and they evolve pretty much passively ever after. We also found that the masses evolve moderately. The stellar masses do not grow very much, and it's not clear whether the models will be able to get that right. It is also very difficult to measure the luminosity or the mass of a brightest cluster galaxy because the halo extends forever sometimes. And sometimes you don't know whether that light belongs to the galaxy or to the cluster. But what we found is that the mass, the stellar mass, evolves moderately, while some of the more active merging models requires the mass to work, to evolve more strongly. The other thing that we found is that the mass, the stellar mass of the brightest cluster galaxy does correlate, but weakly. It correlates clearly, the correlation is there, correlates weakly with the mass of the cluster, okay? So it only correlates if it is a power law to the power of 0.2, 0.3. And it's not very clear that that's what you get from the models either, but that is what you find. So these special galaxies, their stars are old, they're growing in mass moderately, and the dependence of the mass with the cluster velocity dispersion of mass is only moderate. We don't know why yet. But morphologies, I like morphologies. I like looking at galaxies, and I like classifying them, and I like to separate them in ellipticals and S-zeros and spirals and find beautiful gravitational lenses and things like that. And then EDISCs did that with HST, 80 HST orbits, okay? And this is the main result. Some of these had already, of course, been shown before, okay? But we sort of put it all together with a larger sample. And this is the main result, okay? And there are 3 panels here I like and 1 I don't. And my co-authors prevailed over me, and we couldn't take this ellipticals and S0 together panel out of it. So look at the one at the top, the elliptical on the left. The elliptical fraction does not change with redshift, okay? The massive galaxies, of course, we're only talking here about sort of the 2 or 3 top magnitudes in the luminosity function. The elliptical galaxies do not evolve in fraction. They've been there at least from redshift of 1. But the most interesting thing is these 2 plots, okay? If you look at the fraction of the S0s, the fraction of the lenticular galaxies, we find that at high redshift, you find very few. By the time you get to redshift 0, they are probably the dominant, no, they're clearly the dominant population in the clusters. While spiral galaxies do exactly the opposite. I mean, the top and the bottom plots here are mirror images because that one is flat. And I think if I look at that, I cannot but accept that spiral galaxies in clusters might be transformed into S0 galaxies. I don't know how, but I find very little doubt in my mind that that's got to happen. Okay? The morphology density relation is already there at these high redshifts. This is, again, local density. This is fraction, spiral, and ellipticals, and you see spirals far away from the center or in low density regions. Okay. It would be good if I knew how it works. So, okay. So the problem, of course, is I cannot see the pointer myself, which doesn't help. But I just about. So never mind. This is the spiral galaxies, okay, and they disappear at the center, and the ellipticals go up. So there is a morphology density relation already at these redshifts, but it's completely dominated by the spirals and the ellipticals, because, of course, there are no S-zeros. There are very few S-zeros up here, down here, okay? So that is interesting. Again, is morphology. We don't really know what it means, but we know that we need to explain it. I've just gone too fast. Something interesting that you must not forget, and that's what happens when you bundle it all together, ellipticals and S-zeros, is if we looked also at the red sequence of in these clusters, okay? And the galaxies in these clusters, this was work that was done by Gabriela de Lucia. What we found is that the red sequence is not populated equally at all redshifts. What we found is at high redshift, the fraction of faint galaxies in the red sequence compared with the bright galaxies is smaller. So what we're having is we're building in the red sequence, okay? The bright end of the red sequence is built first, and then the faint end is built. Some of that is coming from S0, from spirals that are transformed into S0s, but it's very, very difficult to prove that that's exactly the only thing that is happening there. Okay, star formation. What is the star formation doing with redshift and standard fraction of environment? Here we've got essentially the fraction of galaxies that are forming stars as a function of the cluster velocity dispersion. And that line does not indicate a correlation. In my mind, it indicates an envelope. What happens is that in the top right corner, up there are no clusters. What it means is that the most massive clusters down here, even at high redshifts, these are all EDIS clusters and clusters at high redshift, they have virtually or very few star-forming galaxies, while at low masses, you find them with lots of galaxies forming stars or not. By the time you get to redshift 0 here, you get exactly the same thing. This is a very carefully matched sample from Sloan. It's small because it's nicely unmatched to the E-disks, but what you have is that even at high masses and going down to low masses, you've suppressed the star formation already. What this is telling me is that the star formation in the galaxies in the cluster happens first in the most massive clusters, okay? And when you want to suppress it in the low mass, you need to wait a much longer time. Of course, at low masses, you still have significant fraction of star-forming galaxies, okay? So this is telling us that the process that stops star formation, okay, that eventually will transform those spirals into S0s, as I'm postulating here, happens first in the most massive clusters. It's also important to look at how that star formation behaves as a function of local density in the clusters themselves at these redshifts. And here is again local density of galaxies. This is dense, this is low dense. And then let's look only at the filled points here, which are the interesting ones. First of all, if we look at this is the specific star formation rate, that is the star formation rate per unit stellar mass of the galaxy, okay? The average for all the galaxies in black here as a function of density. And at the center, of course, you find that the galaxies have got very, very little star formation activity. They're forming very few stars per unit mass. Part of this trend is the fact that many galaxies are not forming stars at all. And you find more of the non-forming stars at the very center. But even if you look at the ones that are forming stars, and those are the blue points there, those are galaxies that, yes, they are forming stars, okay? Still see that even for those that are forming stars, their formation declines when you go towards the center. It would be very interesting to know whether this increase at intermediate densities is true or not. But the error bars are still very high, because it would be very, very interesting to know whether when a galaxy first encounters the cluster, whether its star formation increases, at least initially because of perhaps the compression of the gas when you get to the cluster or not. And that I really would like answered, but of course you can see that the error bars are still quite large. So in my mind, what I want is a cluster survey that is about a factor of 10 larger than these 200 clusters instead of 20, and we're working on that. Something else that I want to show is that that star formation suppression activity of the cluster depends on the cluster mass. If we look only at the black points here for the sake of argument, the ones at the top, okay, are the sort of less massive clusters. But the ones at the bottom are the more massive clusters. You can see perfectly clear that, yes, the star formation activity declines when you go towards the densest parts of the cluster. But for the most massive clusters, you've already done it even to farther distances. So again, an indication that in the most massive clusters, whatever is happening, the switches of star formation that perhaps will transform the morphology of a spiral into an S0 happens earlier than in the less massive ones. How am I doing for time? Sorry? Okay, well, I'm not going to talk about this then, and I'm going to move to another issue. One of the experiments that we've done very recently with one of my current PhD students in Nottingham, Yara Jaffe, is we've tried to test that the issue of whether when a galaxy falls into a cluster, you increase the star formation first before you switch it off. Okay? And the way we've done it is by looking at the Tully-Fisher relation. We put slits alongside these galaxies and measure the rotation curves, and then we measure the luminosities and do all the magic that we need to do to end up getting a Tully-Fisher relation. And we compare the cluster galaxies with the field galaxies. Of course, when we do spectroscopy, about 60% of the galaxies that we find are not in the clusters. They're not rubbish. They're the perfect comparison sample for this study. And in these plots, okay, you've got them divided into, at the top, into different redshift ranges. And the first thing you notice is that the Tully-Fisher relation has got an enormous scatter. That's already been found in the field. Spiral galaxies, even at the redshift of 1/2 or redshift of 1, their gas, the rotation curves are really messy very often, and you have large scatter. And what you find is that in those two histograms, we look at the differences in the position of the galaxy with respect to the Tully-Fisher relation. That is, at a fixed mass, we find the luminosity. Why we do that? Well, if a galaxy, when it falls onto a cluster, goes bang for a while and increases the star formation, then you would expect it to have an excess luminosity for a while. And those are the ones that you preferentially select because you select in magnitude. Well, as you can see in these two histograms, the red one is the cluster, the other one is the field. In the two redshift ranges, there is absolutely no difference. So this leads me to believe that there is no real bang in this process. However, there is always a however. One thing that we did was to look at how good the rotation curves are. That is, how good the distribution of gas or the kinematics of the gas is in a cluster. And we did that by visually, morphologically classifying each rotation curve, fit, etc. And what we found is, and I'm going to talk only about this one, this diagram at the bottom, is that if you look only at the red and the blue line, the fraction of bad rotation curves, the fraction of disturbed gas kinematics, as a function of luminosity, if you look at it here, for the field, which is the blue line, is constant. That is good because it's telling us that our ability to determine bad or good morphologies does not depend on the luminosity, because you can say, well, the faint ones you cannot see, the bright ones you can see better. No, it does not depend on the luminosity because we are quite conservative in our sample. But in the cluster, the fraction of disturbed kinematic morphology is much higher than in the field. This is hot off the press, and the numbers may change a little bit, but we think that this is robust. That's kind of good, right? Because you expect that something that comes into the cluster gets kicked about, and then you think, okay, the kinematic morphology has changed the movement of the gas. Except, and please answer us on a postcard, if you know why the most massive ones, the most robust galaxies, the ones that should be strong, are the ones most affected. The fraction of kicked about gas, or the galaxies with disturbed morphologies, is larger for larger galaxies. I don't know why. Perhaps because they have got larger cross-section. I don't know. Anyway, that is where we are, okay, from e-disks. And I want to say a few words now about stages, which is, again, a reasonably large collaboration led by Megan Gray in Nottingham, in which many of the authors are listed here. Somebody like Carlos Hoyos in the audience, who, by the way, has got a very interesting poster over there on how to calculate merger rates in a very clever way. It's over there, so don't miss it. I'm just gone the wrong way. Again, it's a study of a reasonably nearby structure at redshift 1.2, but it's a very large structure that contains 3 clusters and several groups and a very large field. And again, we've thrown at it as much observation as we can. Okay? It's a very large field of view that contains 3 able clusters and a group at the bottom. It's about 1/2 a degree by 1/2 a degree, and it has been image. This is just to tell you how big it is. And this is to tell you that it is a very large ACS HST imaging survey with all that many pointings. Okay? So one of the things about it is that is part of the Combo 17 initial study. For those of you who are not in the field, Combo 17, what it did is use 17 filters to get a sort of low-resolution spectral energy distribution for the galaxies. Now the Alhambra project is trying to do the same thing with even more filters, but that allows us to have very precise photometric redshifts that tell us whether the galaxy is in the cluster or not, and a lot of information about the photometry. Okay, now, because we've got lots of data, okay, when trying to find which galaxies are forming stars and which galaxies are not, we are not just relying on one color like G minus R. No, we've got ultraviolet, we've got infrared, and therefore we can see what star formation comes in the ultraviolet, what star formation is extinct and we need to see it in the infrared, etc. And if you do that, your selection of galaxies is better, and you can separate and find 3 populations of galaxies in this cluster. One population in which you have them, they're just red, okay, and they're not forming stars. Some of them are red and forming stars, and some of them are blue and forming stars. So these are the ones, the standard spiral galaxies that are forming stars. Nothing special about them. The red ones that are not forming stars are typical S0s or elliptical galaxies. But these are a very interesting population of red, dusty spiral galaxies. They're red, even though they're forming stars, because they've got a large amount of dust. Or so it seems. It seems as if they've got more dust for the bang. That is, for the amount of star formation, they seem to have more dust. What do we think is happening? What we think is happening is that the star formation has been reduced. It has been reduced from the outside in. So it's reducing to the outside. The center of the galaxy contains more dust, and whatever star formation remains, which is about half of the star formation of these ones here, is more hidden by dust. So what do we know about these galaxies? Well, the way we interpret them, with the help of other observations, for instance, the observations of galaxies in Virgo and other places, and the work of people like Chris Moss, who very sadly died a few months ago. Those of you who knew him knew how fantastic a person he was. Anyway, what people have found is that in present-day clusters of galaxies, what you have is that the star formation is more concentrated than outside clusters. This is telling us that the star formation switch-off process happens first in the outskirts and then propagates inwards. And then what you have is the fact that because the star formation continues longer at the center, that helps us a little bit if we want to build the bulge that will help us build those lenticular S0 galaxies. And this also links with something else. Just look on the right-hand side here, because I don't have time to go through the other bit. What you find is that this is linked with a large population of red spiral galaxies. Now we've got Sloan, and we've got hundreds of thousands of galaxies, then we can look at populations that are perhaps less abundant. And there is a large population of red morphologically spirals that has been done using this fantastic project that is called Galaxy Zoo. And this work was led by Stephen Bamford in Nottingham and Portsmouth at the time. And what they found is there are many spiral galaxies in the present-day universe that live in high-density environments. Again, here they are, density and fraction of red spiral galaxies. They live mostly in dense environments. And those galaxies, we think, are the next stage. The first stage, you got the spiral, forming stars being blue. Then the star formation switches off in the outskirts, and they are redder because the dust is concentrated at the center. And then they switch off completely, and you get into red spiral galaxies. One interesting thing is here on the left, and I'm actually going to talk about it. If you look at the dependence with density of on the top left of the galaxy population, you can see that the non-forming star galaxies, of course, live at the very center. The forming stars live farther away, that is, where the density is lower. But here, the green line, which corresponds to those dusty spiral galaxies, those that have got a reduced star formation, but they look redder because of the dust, they seem to live mostly at intermediate places. So this process that switches things off seems to happen when the galaxies approach the dense regions. And it seems as if by the time they settle down to live in the center, they are mostly red. Okay? So this is pretty much what I said, a summary of what I said. Spiral galaxies fall into clusters. Something, and I wish I knew what, switches off star formation. It does it outside in, because there is a residual star formation at the center, and not so residual, it may build up the bulge. That region has got more dust, so you see it to be redder. They become then S0s. Interestingly, we've also looked at whether in this process, the disks of these galaxies change in structure or in size. And the answer is, and this is work that a current PhD student of mine, David Maltby, has done in Nottingham. We look at the size-mass relation of ellipticals, spirals, and S0 galaxies as a function of morphology, and there is no difference whatsoever. So whatever is happening is not changing the size. There is one mild effect, and is that in the lowest density region, you find galaxies like the ones on the top row, and those are galaxies with fragile-looking extended disks. So it seems as if your disk is fragile and extended, and these galaxies are only low mass, they do not exist in clusters. Those seem to have been broken. But even when you look in terrible detail at the profiles of these galaxies, of these disks, and look at how the light is distributed, whether the profile breaks or not, what is the extent of the disk, there is no difference with environment. So this is telling me that whatever process is switching off the star formation, it must be quite gentle. It doesn't break the disks. Not only doesn't break them, it doesn't do too much to them. So I don't know what it is. So this is the summary, okay, and I'm going to read it from my screen because I cannot see it from there, and says that the spirals transform into S0s in clusters. I don't think there is much doubt in my mind about that. Massive galaxies do that earlier, okay? It also happens earlier in massive clusters. And the driving mechanism must be quite gentle. Does it all fit together? I think it does, okay? We can see from the Galaxy Soup project this beautiful sequence between spirals to red spirals to S0. So I think everything fits together, but there is a but here. There's always a but, and is that I really would like to know what the mechanism is. But whatever the mechanism is, it is a gentle one. And I'll finish here.
I have a couple of questions. Maybe I will start just with one, and if somebody wants to do another one. So in one slide in the middle of your talk, it seems that you wanted to convince us that there is no enhancement in the star formation when a galaxy is falling in the cluster, or
at least from Tully Fisher, that's correct.
My question was going to be at that point that it doesn't. It seems that it's not consistent with what we are finding at redshift 0.81, and we are seeing that luminous infrared galaxies live in not very middle environments. Yeah. And that's very similar to what you have shown in a later slide. So I don't know if the picture is as consistent as you claim.
It may not be. Actually, Alan Dressler pointed exactly the same thing last Monday. So there's two things. One is the Tully Fisher test has got the problems of dust. But there is another problem that I see, okay? If you got an infrared luminous galaxy, is luminous with respect to something. You normalize it, I don't know what you normalize it to stellar mass, to what?
Well, this is a high luminosity, a high star formation rate galaxy.
Right.
So
But
we're talking about 100 solar masses, so it's not exactly the same as you are seeing in the local universe.
Yes.
It's not a dusty spiral with less star formation than a normal spiral. This is a spiral because the morphology is spiral-like at redshift 1 or so, but it's forming stars like crazy. So
Okay, I mean, we've got virtually very few of those in here. There are not many in these clusters. Maybe because these are real, very dense clusters rather than sort of a more gentle distribution, and the densities may be different. But the thing may not be completely consistent. I agree, and I would like to know. But that's what Tully Fisher tells us.
Alfonso, pointing in the same direction than Pablo.
Yeah.
In the plot that you saw that the fraction of bad galaxies in terms of the rotation curve are the brightest one.
Yes.
So this is not a direct indication also of the same thing. So the brightest galaxies, I mean, if you saw the same plot, but instead of using the luminosity, using, for example, the stellar mass.
Yes.
So this is, I mean, I would really like to see that plot in that sense, because maybe the excess of luminosity is just an indication of a brightness due to a new star formation.
It is possible, but we are looking at that, and that's hot off the press, and we are correlating the fraction of bad galaxies with enhanced star formation, with specific star formation, and I don't have the answer yet. Yara is working very hard on that, and we've got a draft circulating within the collaboration, and that's one of the things we're going to look. And that is true, and that goes back to Pablo as well. Maybe what happens is the ones that for which we can actually put in the Tully-Fisher relation, because of course the bad ones we cannot put in the Tully-Fisher relation, and we cannot do the test for that. And maybe that is the ones that we've thrown away from the Tully-Fisher relation, the ones that are enhanced. So we're looking into that.
Well, there is another thing, is that you are getting conclusions from very nearby clusters, and you're talking about an evolution that maybe happened at redshift 1.
No. This evolution of morphological happens at redshift 0.4.
0.4?
Yes.
But still at redshift 0.4, 0.6, 0.8, the luminous infrared galaxies were much more numerous. So,
Indeed.
So maybe we are missing something because we are looking at very nearby clusters, and we should be...
I think it's a very interesting discussion, but maybe you can continue later, because I'd like to take the last question.
Okay, one quick question, Alfonso. So you were wondering what makes these spirals, these red spirals.
Right.
So if you take a spiral in the field, it's still growing today because it has gas cooling from a hot reservoir, and I can tell you there's
that's what you tell me.
So
yes.
the first thing that I can show you evidence, but the first thing that happens when a galaxy falls in a cluster is that hot reservoir is stripped.
Yes.
Now, so
I like that very much.
Right, but you could look. Is there any evidence from X-rays that this may be what's happening?
Oh, there is plenty of evidence from X-rays.
I don't mean ram stripping of the cold gas, but of the hot gas.
Yeah. From X-rays, there is evidence, quite reasonably new evidence that the hot gas is being stripped. The cold gas, as you know very well, people like Kinney have looked at it, and it also happens on the outskirts. But of the big hot halo gas, there is evidence that happens. However, what is not very clear is whether it happens to enough galaxies to explain it all. So that's why I sort of stepped away from actually telling you what the mechanism is, because I didn't have time. But I quite like that idea, and I think that is gentle enough to fit the rest of the bill.
Okay, thanks again.